Welcome everyone to this webinar on engineering design, simulation, and optimization in the cloud. Thank you very much for joining us today. My name is Valerio Marra. I'm the VP of Marketing at SimScale, and I will be your moderator today. Today's presenters are Victor Pimenta, Mechanical Development Engineer at Withings, and Steve Laney, Application Engineering Manager at SimScale. Victor has a degree in mechanical engineering and specializes in design and manufacturing for the medical devices industry. Steve has a degree in mechanical engineering too and a PhD in material science. And before joining SimScale, he worked in aerospace design and in engineering simulation. Let's take a look at the agenda for today then. Next slide, please. So after this very short introduction, Victor will discuss how he designed and optimized a snap fit design used in a portable medical device. Great application. And it's almost everywhere. And then Steve will dive into the demo, showcasing a snap fit simulation project running this SimScale platform. It will basically show the simulations build, comment on it, and on the numerical results that we achieved. After the demo, we will run a Q&A session, and we'll discuss also how you can get to try the software for yourself. And please do not hesitate to ask any questions at any time during the webinar. There's a chat box in the webinar panel, and you may do so again during the webinar or during the Q&A. That's okay. All right. So this is all for the intro and for what we're going to cover today. And now over to Victor. Thank you.
Thank you very much. So it's a pleasure to be here today. It's a great opportunity to present this case study with SimScale. And first of all, I'd like to introduce a little bit about Withings. So we're a medical device company based in France, and we design and manufacture a wide range of products from smart scales to connected watches, blood pressure monitors, thermometers. And we've been in the market for more than 10 years. And we always deliver products that combine a sleek design and great function. And all of this with embedded medical features. So this is a way to empower our users and ensure they can take control of their health while having a great experience. And this is also the case for BPM Connect, which is our blood pressure monitor developed with the help of medical experts. And it has an appealing design, best-in-class blood pressure measurement, but it also comes with many electronic components inside of it. So space needs to be optimized. We as engineers must then optimize how we integrate these different electronic components with assembly, and that's where snap fit joint designs become valuable, and this is very important to notice. I will outline why in the next slides. So first of all, as you can see in the right-hand side, it consists of a plastic molded geometry that can be used to clip together two different parts. So they are the two parts at the top corner of the right-hand side. And there are many types of snap fit joints. For this webinar, we are just going to discuss in more depth about the cantilever hook type. It is a lightweight feature which allows for the assembly of two parts together, as you may see, without adding any additional fasteners. So this represents a lighter, finer product and a cheaper bill of materials because we don't need any screws or all the metal fasteners to make it work. Moreover, it's easy to deploy design because it can be mold injected, and it doesn't require any post-processing, which leads to less assembly steps and a more efficient integration. This is very good for, let's say, a quick assembly into factory. However, when it comes to some disadvantages, it requires a precise and optimized design to work correctly. So that's what we're going to talk about in the next slide. Most of the times, the CNC machine and 3D printed parts don't reach the same performance as a mold injected and mass-produced part. This is mainly because current technologies are still not able to reproduce the same inner structure, the orientation, the grain of the material of a mold injected part. Also, it is important to notice that physical testing is costly and it doesn't allow for a sectioned view of the part. But the good news is that SimScale can provide with good numerical simulations and that we can visualize every section of our snap fit joint together. Finally, we are going to look for a design that combines an appropriate mating force so that the product can be assembled. We are also checking for the clip deformation. We need to keep it in elastic region. We don't want to have a plastic deformation. And a very important point as well is the cost-effective testing, because we cannot just prototype infinite versions of many designs. It's simply not bearable. So that's where numerical simulation, mechanical simulation comes in, and enables engineers to reduce the number of prototypes, as we can further optimize the joint section for each round of simulation and launch more intelligent designs for prototyping. As a result, we have much shorter design rounds. That's the focus of this presentation. So we could do more intelligent prototypes and quicker prototyping with SimScale by doing section views and mating force calculations and enabling a better results visualization. And there's also a point which is a big advantage, is that it enables the mating force calculation. This is very important for a DFA, so a design for assembly approach. In this specific case study, we will analyze a snap fit joint assembled to an electronic board. So if you look at the right-hand side, we have our product, the BPM Connect, a blood pressure monitor, and we are going to take a tiny section of it, which has a clip. So you may see the cantilever hook at the bluish video with a plastic casing going to be assembled to a PCB. So to summarize, our simulation will look exactly as the video on the right. And this is reality. So we also had this case in real life. So a plastic part must be assembled to a PCB, an electronic board. And this is a white casing. This is the shell that we have here. And this is a static structural simulation, but it has a nonlinear setup, as the stress distribution is going to vary with time as the two parts are gradually assembled together. So as the plastic casing moves up, the PCB is going to have different stress distribution with time. The boundary conditions are quite simple, but we need to be rigorous while upon setting them. So we set a formula-based displacement or maybe a table-based displacement. It depends on the use of the simulation. And also, we are going to fix one of the walls of the PCB because this is the real design. So we need to have an assembly that doesn't move. So we ensure that it doesn't float. The corners are going to be refined in the mesh to allow for precise calculations because, as you may see, we have some sharp corners, some radius at the base of the clip. And this is a very important step for mechanical simulation. Finally, at the end of the simulation, we'll be able to obtain the mating force of this joint, as well as to check if the deformation is acceptable for the chosen material. That is, if it's still in the elastic region of this material. Then we move on to the contacts. And we need to define a physical contact to avoid the overlapping of these two parts during their assembly. As the plastic casing is going to move up, we don't need it to overlap the PCB. We need to exceed the PCB and then mate the upper surface of it. So this is required to ensure the mathematical calculations behind the simulation succeed and to obtain realistic results without any overlapping. For this case, we chose the penalty coefficient method and set its parameters according to the material properties involved. So the coefficient is a mathematical approximation, and we can find many ways to define it. About the master surface, it's going to be defined as the electronic board, while the moving part will be the plastic clip. So the plastic casing is going up towards the PCB. And then we'll have 4 boundary conditions. To ensure that the plastic part will move, we'll set a displacement formula for it or a table formula for it. And to keep the electronic board fixed, we'll assign its top surface to a fixed value condition. Finally, we will also cut this part, this 3D model in half, as we can simplify this problem to a symmetric geometry. This would lower significantly the runtime and reduce the computational cost of the simulation. Finally, we set an elastic support at the electronic board because it doesn't touch the plastic part of the initial step. So these two parts are apart from each other at the time t equals 0. So we need to set this to stabilize the simulation and to keep the PCB from floating in the schematics. Then we can move on to the demonstration of this simulation.
Okay, so let's have a look at SimScale. All we need to access SimScale is a web browser, and from there we can get to the SimScale homepage and the dashboard that contains all of our projects. This essentially gives you an SPDM system to manage all of your data with unlimited storage for your simulation needs. We can see latest jobs and account history, as well as a searchable list of all of the recent projects. So if we search for the project we're going to have a look at today, it's this snap fit from Withings. And we're going to have a look at some nonlinear FEA analysis of this snap fit. Okay, so as we introduced in the slides, we can see here the casing and the base and the snap fit connector, the single-use snap fit connector that holds all of this together. And the question that we're looking to answer here with the simulation is, what is the insertion force to insert this connector? What's the extraction force to actually pull it apart? So how resistant is it going to be to coming apart? And what are the effects of different tolerances? So we've analysed this snap fit at the assembly tolerance, so with all of the parts at their drawing tolerance, the nominal tolerance, and also the assembly tolerance. So this is as it's designed to work. And we can see it's snapping together nicely here in the animation. So if we go to the peak stress point where the snap fit is just about to snap back over, we can have a look at the stresses that we've got here. So we've got some peak stresses down in the tang, and we could pick out what some of these are. So, we've got stresses of up to about 13, 14 megapascals, and we can obviously highlight regions of stress with the isovolume as well. So the thing that we want to look at here is if we've got maybe a minimal tolerance, so a worst case scenario for the stress of this clip, where the part is slightly smaller than it should be, and we've actually got these two parts closer together, what's the stress going to be in this actual clip? So we can have a look at that by comparing the assembly tolerance directly with this one that we've analysed here as well. Okay, so on the left we can see the nominal assembly, and on the right we can see the worst case scenario with a minus 0.1 millimeter assembly tolerance, and we can see a much larger stress region in the tang due to that assembly tolerance. So it's really great to be able to analyze these side by side and see how the two compare. Obviously, we can also get some detailed analysis out of here from the phase calculations and volume calculation. So we can see what the reaction force is required for this actual snap. So we can see that we've got about 1.2 newtons to connect the parts, and a very similar 1.2 newtons to break the snap apart as well. And we could also analyze the peak stresses that we've got in the part as well. So if we compare that to the minimal tolerance, so it was 1.2 newtons for the assembly of the nominal tolerance, but for the minimal tolerance we've got a slightly higher, almost 2 Newton force for snapping the part together and extracting the snap as well. So again, very useful to be able to see these side by side. So how did we actually get here? Well, I'll take you through how we set up this simulation. So the first thing we need to do is add our geometry. And in this circumstance, we're using the geometry directly from Onshape. And we can see the various parts we've got in Onshape, and we've got variants of the model in Onshape. So from this, when it was started to be created, we've then got assembly tolerance minus 0.1 millimeters and plus 0.1 millimeters assembly tolerance. So we've reviewed the minus, and we'll have a look now at importing the plus 0.1 millimeter geometry as well. Okay, so that's imported our geometry into SimScale. So up here now we see a third geometry, And I'll just tidy up the naming a bit here. So we've got our assembly tolerance plus 0.1. And we'll then be able to use this to set up another simulation. So the great thing about associativity between these CAD parts is we don't have to go through assigning everything again. We can take the minus 0.1 millimeter, use that as a template, and then swap out the geometry for the plus 0.1 millimeter case. So SimScale sees that we've got some contacts, say that we want to keep those same contacts, and we've got associativity between the geometries. So all our material assignments, etc., are preserved. So in the matter of seconds there, I've imported a new geometry for a different simulation, and we can immediately start that simulation running. I get a warning that I've got no load defined here. That's fine because I've defined a displacement. So we can start that new runoff now. And while that's running, I'll just show you the steps that we've gone through. So this is actually the plus 0.1 assembly tolerance. And we'll give that same name to the simulation that we've got running now. Okay, so how have we actually set up this simulation? Well, let's work down through the tree. So first of all, we've got physical contacts defined between the parts that we expect to contact during the simulation, and we're using a penalty method for those physical contacts. And this is a nonlinear analysis because we've got the movement of these two parts respective to each other. For the material properties, we're using an epoxy for the base plate, a linear elastic model, and a polycarbonate for the other component. Again, linear elastic, we don't expect the stresses to go into the plastic regime of these materials. And then we've got the boundary conditions. So we've fixed the base plate here for snap assembly in position, and we're assigning the displacement to the mating part, and that in this circumstance was done using a table. So we've defined over time at 0.5 seconds it will insert 0.004 meters in the Z direction, and then it will extract at 1 second. And then we've got some elastic support and supporting structure that simulates the remaining structure that constrains these parts in place. For the mesh that we're using here, we've actually stuck with the original standard mesh settings. It's a physics-based mesh, so we don't need to worry too much about this. The standard settings give us a nice balance between simulation time and accuracy. So we can see on this base plate we've only got minimal refinement at this end, but where we've got the contact it's slightly more refined. Okay, and coming down now we'll have a look at the simulation. That's nearly complete. So the other thing that we've done here is we've added the result control. So this allows us to get some analysis out, such as the area calculation for the sum of the reaction force, the volume calculation for min and max stress, and the average stress in that component. So our simulation is completed. It's completed there in 3 minutes and 0.3 core hours. So now we could obviously post-process this just like we did with the other ones. So we can have a look at our simulation, go to the 0.35, time step to see the stress that we've got, and just format this so it's equivalent to the others that we were looking at, and we can see that the stress there is much lower in the part, to be expected because we've got a larger gap between these two components. And of course we could directly compare that with the nominal or the lowest assembly tolerance. So it is in fact much lower stress than the nominal assembly tolerance. So it'd be interesting to look here at what the actual phase calculation gives us for the reaction force. So yes, much lower, only about 0.7 newtons to actually mate the two parts, and also only about 0.7 newtons to pull these apart. So with this assembly tolerance, maybe we would have a problem for this product in service where the two parts would disconnect, but that's what's really powerful about being able to simulate this. Okay, thanks. So let's have a look back in the slides now at some results that we saw in the demonstration. So comparing all of these side by side, we can see with the maximum tolerance, the plus 0.1 millimeters, we've got very low stresses in the part, but critically, we might have too low a force required to break the snap apart, and we could have disassembly potentially. So it's really powerful, as I said, to be able to compare this and do these simulations without having to create a prototype and run physical bench tests. With the nominal drawing tolerance, this snap fit is performing as we would expect, and we would have obviously been able to hone this design using SimScale to get the optimal performance here. And at the minus 0.1, so the bottom tolerance, we do have some reasonably high stresses, and there is a risk that we would actually exceed the plastic yield of the material in these regions and introduce permanent deformation. The other concern here is if we're at bottom tolerance and there's a very high force required to assemble these components, it's an ergonomic concern potentially for those people that are assembling these components on the production line. So it's always a very important thing for snap fit. And I love this graph of the 3 insertion and extraction forces. It shows really nicely with the different tolerances, the force required to mate these two parts together. So obviously in yellow, we can see the one with the largest gap with the lowest force, about 0.7 newtons. The nominal up at about 1.6 newtons, and the minus 0.1 millimeters up at about 1.8 newtons. So obviously, we've seen a great introduction from Victor there about how Withings are actually using SimScale, and we've been through this case study. So why use SimScale? Well, with SimScale, you can simulate early in the design process. You can simulate more, and you can simulate now. SimScale makes high fidelity engineering simulation technologically and economically accessible to anyone because we're leveraging the capabilities of the cloud. So you don't need to have the expensive on-premise hardware. You don't need to have expensive software that you're maintaining, installing, etc. It's all powered by the cloud and you can access it from anywhere. We provide a high accuracy, high fidelity solution that gives you results very quickly. So you saw in the demonstration, we had results back there in about 3 minutes from that simulation. So very, very quick response. And we enable engineers to simulate without compromise. We provide streamlined workflows and in-product collaboration, so you can share projects with your colleagues. This really differentiates SimScale because there's no data files to transfer. If I want to share this project with someone in North America from Europe, With traditional simulation platforms, that would mean transferring gigabytes of data over the internet. With SimScale, it's all in the cloud, so it doesn't matter where you access it from, you're accessing the same data, so sharing is instantaneous. And we deliver all of this with best-in-class solvers and a nice UX on demand. So I'm just going to talk slightly now about the SimScale ethos and the cloud-native, collaborative, end-to-end simulation platform that we provide. Traditional simulation tools are focused at the end of the design cycle. So they're typically used to validate a design when it's already been conceived. And in some cases, tooling may have already been manufactured, and the cost of change is typically quite high at the end of this design cycle. There's various training and support required. There's obviously software licenses required for these software tools. There may be a job scheduler, middleware for HPC orchestration, and high performance on-premise hardware that is a depreciating asset that needs to be maintained. SimScale can do this late design process as well, but SimScale is also suited to the early design process, working iteratively in the design process, evaluating designs before they've reached a late maturity in the design life cycle when the cost of change is small. You can generate a much better design quicker by simulating earlier in the process, working out what the best things are to do. Obviously, simulation fits into various other parts of the design process as well, but we see the early stage design process as one of the most important and where simulation should be used more. So with SimScale, you don't need to worry about all of the infrastructure. We take care of the HPC orchestration and everything that goes along with that, the network storage, the housing, the load balancing. You don't worry, you just log into SimScale and you can use it. On top of that, we have best-in-class simulation technologies that you can make use of. So this leads to the different applications that you can simulate. There's various mechanical, eigenfrequencies, harmonic response, impact, crush, etc., FEA cases that you can simulate. And you can also simulate things like thermal stresses, conduction, radiation, heat transfer, and convection. And then we also have flow analysis capabilities. So this could be external flow for, might be for AEC, external aerodynamics for a vehicle, or internal flow of a valve body, for example, rotating flows, multi-phase, and mixing. So SimScale, as we said, is fully accessible from the cloud, a SaaS application that provides you access to all these technologies. And we have an API that spans over this, so you can build workflows using other tools integrated with SimScale. And today we've obviously seen a stress and deformation, solid, implicit FEA simulation, leveraging these parts of the SimScale suite. Okay, so that's everything technically from us today. I'll hand back over to Valerio for the Q&A session. Thank you.
Thank you guys for presenting. Thank you, Victor. Thank you, Steve. And now it's time to take some questions from the audience. We'll do our best to answer all your questions in the remaining time, and we will get back to you after the webinar in case some will go unanswered. All right, so let's start with Victor. So Victor, this question is for you. So the engineers in the audience are curious to see how you define the penalty coefficient.
Oh, so that's a great question. So first of all, we had to define a prediction for this coefficient. It's about 5 to 50 times the Young modulus as a rule of thumb. But what we need to know is that the bigger this value is, the harder the contact is. So it really avoids the overlapping of the plastic casing and the electronic bore. And in this case was very important for our design, so for our project prototyping, because that's where simulation is powerful. We could predict the design performance ahead of production. So there was some overlap and some stress concentration over the round corner at the base of the clip. And by setting a correct penalty coefficient, we could predict this ahead of production and prototyping. So as a rule of thumb, let's say about 50 times the young modulus of the softer material, or the average of the young modulus of the materials involved.
Thank you, Victor. Thank you for the answer.
That's
This
right,
one,
yeah. Sorry, Valerio,
please
if I
go
can
ahead. Please
just
go ahead.
add slightly to that. One tip we have with the penalty coefficient for the person that asked that is it can be a bit of an iterative process. Once you've run a simulation with the range that Victor recommended, 5 to 50 times the youngest modulus, you can check the post-processor, see if you've actually got some false penetration of the components. And if you do have that, you may need to increase the penalty coefficient slightly. We typically do this by about 5 to 10 at a time, until you get to the point where when you post-process it, you don't see significant penetration, and you know that you've got a nicely converged result with the correct penalty coefficient. Thanks.
Thank you, Steve. That makes sense. Otherwise, all the forces and other parameters are going to be off. And that's a question for you then, Steve. Sorry, go ahead.
Yes, also there is a good point about SimScale is that we can really check the solve log live. So it's we can really see if the residuals are high. We can see whether the overlap is happening between these two parts. So it was somewhat easy to define it with the iterative process of simulating this part. So as Steve has well said, we can really iterate over the penalty coefficient as well and over the design. So it's a process that it's really interactive with the disintegration between Onshape and SimScale. It was very helpful to have this associability between the two platforms.
Got it. So I'll stay with you then, Victor, because lots of questions are coming in. Because there was a question around how you created your geometry, if you could change it during the simulation process, and then also how you meshed it.
Yes. So for this part, actually, we had to define first of all the physical context, and it was a very important part of the problem. So the PCB was, let's say, a stiffer part in the simulation. The plastic casing was pretty much flexible, and then we had to assign it as the master surface. So we have defined it as the, let's say, the focal point of our simulation. Therefore, all the nodes from the plastic casing were constrained to the master surface, so to the master entity, which was the PCB. And to match it all, we had to define what are the points that are more fragile and what are the points that are sharper than the others. So, for instance, in this clip, we had the head of the clip, so the undercut, and that's where we try to improve the node length and also try to, let's say, combine a good physical contact definition and a more precise mesh. And in this case, it was a fine mesh. We could simulate this very quickly and get results in less than hours. So comparing to traditional techniques, let's say if we had to prototype it, it would take maybe some weeks, and we had shipment time, and we have a lot of lead times to sum up. While with simulation, we can have a result in some hours, a few couple of hours, and launch a more intelligent prototype. So all this process was orchestrated to help us and to shorten the design round of this part.
Got it. Thank you, Victor. And for you, Steve, I'll condense two questions in one. So the first part is if the project that you showed can be made available to the people who were in the audience, they can basically copy and make it their own. And then the second part of the question is if other geometries could be imported, right? If they don't use Onshape, what are the possibilities there?
Yeah, thanks. They're really good questions. So often when we run webinars at SimScale, we do make the model available. In this case, because this is Withings geometry, we won't be making this project available to be freely used. However, there are plenty of similar simulations available. For example, if you search for plastic push pin in the community projects and look for a project by D Short, is a very similar snap fit assembly of a plastic push pin. Maybe we can add a couple of links to the follow-up email, Valerio, to cover that question.
Yes, let's do that. Good idea.
Okay, great. And the other question, obviously, we were showing the tight integration with Onshape here, because that's the CAD tool that Withings use, and it's a fantastic way of being able to have a whole workflow from design to simulate in the cloud, get your geometry into SimScale through there. But we're not only integrated with Onshape, we support any CAD format. SimScale is based on a Parasolid kernel, so any of the Parasolid kernel CAD systems are supported extremely well, like SolidWorks, for example. But we also support other proprietary formats from NX or CATIA. So yes, we support all the intermediaries as well, like STEP or IGES.
Thank you. Thank you so much for the answer. One more for you, Victor. So why is the plastic casing moving rather than the other part, which I guess is the PCB?
So in this case, it's linked to the physical contact. As the PCB is the more rigid part, as it is a stiffer part, we define it as the master surface. So it's a fixed, let's say, entity. In this case, it still can deform, but in this case, the plastic casing was the part with more deformation. So all its nodes, from the physical contact definition to avoid any overlap, to ensure that the mathematical calculations succeed, find as the slaves find, for instance, all the surface from the plastic casing contact with the PCB as these slave surfaces.
Got it. Thank you.
Yeah, as a rule of thumb, the more rigid part usually and the steel part surface are considered as the master surface, and it was much easier in this case.
Makes sense. Thank you. That's a good practice after all. All right, one more question. We need to be aware of the time, and that's for you, Steve. Is if we can run multiple simulations in parallel, and how long did it take for this simulation that you showed to run?
Yeah, great. So this individual simulation that I showed in the example here, it ran in 3 minutes. We were using the standard mesh settings. You could obviously do a finer run to get higher fidelity results. But for the comparison that we were running here, a quick simulation was perfect. And so we got the results back there in 3 minutes. And yes, of course, you can parallelize as many simulations as you like in SimScale. Every simulation that you start is started on a new cloud VM in the cloud. So you can set off 10, 20 simulations in parallel, and it has no impact on your desktop machine that you're using because all that computation is being done in the cloud. So it's a real advantage of SimScale being able to run all those simulations in parallel.
Got it. Thank you. All right, and that's all the time that we have for the questions today. But we do have one more slide, and but before going to the slide, allow me to thank our presenters, Victor and Steve, and also thank the audience for engaging with us today. All right, and now let's go to the next slide, which is the last one. So this is how you can get in touch with us and get a personalized demo or start to using the software. We'll get back to you very quickly. Alrighty, so thanks again to the audience and to Victor and Steve. In case you guys want to say hi to the audience, now is the time because we're going to close the webinar now.
Thanks, Valerio. Thank you to everyone for attending, and thanks for the engagement.
Thank you very much for this great opportunity. It's a pleasure to be here.
Alrighty, thank you so much. And everybody, have a great rest of your day. See you soon.
Bye.